Cloning a graph. Given a reference of a node in a connected undirected graph, return a deep copy, which is just a clone of the graph. Each node in the graph contains an integer value and a list of its neighbors. And it's important that it's a list because that means we can't do like constant time checks to see if something's in it. That actually doesn't matter for the implementation of this algorithm, but that's just something interesting to note. Is it's a linear time lookup list, and in C++ they do it as a vector. And then they got some simplifying things you can keep in mind. Each node has a unique value. I mean, they have a unique address too, but they have a unique value, so that is an option to identify a node by. And then their examples, they got some example input, and they have some edge cases that they want to remind you of, I guess. These aren't interesting, but they're there. Another thing to note is that despite, okay, so we're making a copy, meaning we have to allocate some memory, and it's not a multi-graph, but it can have loops. And the loops thing is that's the difficulty of this whole algorithm. It's dealing with loops. And when you have a loop, you have the same node listed as a neighbor multiple times, but we're going to need to have one chunk of memory, so they're going to need to have the same address, but be listed in multiple nodes, lists of neighbors. So as you can probably guess, it's pretty much depth first search or breadth first search or any kind of graph traversal you want. Our target runtime is going to be linear. We're going to visit each node once and do some constant work each time. That's pretty obvious. So the difficulty in this is arising in the implementation and keeping track of what you visited and dealing with that appropriately. Yeah, so let's get started. First things first, we're going to need a visited something to keep track of what we visited. Since the graph and not a tree, trees you can get away without that, but visited visited somethings, you could either do you want to do something hash based, so you can have that constant time, and well, theoretically it's not constant time, but in any good implementation, which in C++ it certainly is, especially in the modern ones, but I think it's pretty much always been that way. And I know Python, as of version 3.4, they adopted some cryptographic hashing, so that's constant time lookup. In the vast majority of cases, you could get some weird ones, but that's in most applications, that's not something you need to worry about. But that's something to keep in mind. It's hash based, and you need to do this lookup of what you visit. So it's either going to be a set or like a hash map, which in some languages might be called a dictionary. In this one, it's still a map in C++. Okay, I'm gonna get to the data type in a minute, and I'll come back to that. Normally, okay, I'm going to recommend going with the recursive depth first search approach, if for no other reason than keeping the code a little bit smaller. You could certainly do it iteratively. You could do depth first search iteratively. You could do breadth first search iteratively. I think you could maybe do breadth first search recursively. Probably not, actually. No, I don't think so. Not really. It's not as easy. If you can, it's way wonky to do recursive breadth first search. So recursive is going to be more concise. You wouldn't necessarily want to do that in production code, because then you run into limits of stack frames, which are only in the tens of thousands, which doesn't scale super well. But for the purpose of an interview, I recommend going with recursive approaches because they are smaller, and smaller is faster to write, and that is good. That is A-OK. All right, so first things first, let's check for edge cases, because our input is a pointer. I mean, they give you this, but depending on the company, they might not give you these to start off with. But our input is a pointer, so we check for null. If not node, return 0. And also remember, you might see keywords like this, or remember these both resolve to 0. These are just literally, these are 0. They're literally 0. Uh, yeah, maybe your interviewer cares, maybe they don't. If they say something, then just, mention that it's 0, it's null, same thing. That's probably good enough. Okay. I often recommend for these kinds of things, like recursive functions, I would say make a separate function and then have the main original function. All that does is kick off the other one that does all the work you want. And that other function would be in the format that you want. It's going to have the signature you want, the return type, the arguments. In this particular case, I think this is already a good format. So we don't need to do that, which saves a little bit of space, a little bit of reasoning. It works out okay. Um, what I'm gonna do is, how do we deal? I'm trying to get at what is the data type for this visited array? Is it like a dictionary? If so, what do we track? Or can we get away with just a set and not dealing with key value pairs? And it's how do we deal with when we visit, so say we start at this one here, we're copying that. We're going to add the 2 and the 4. We're going to make clones of 2 and 4 and add those to its output. And then we're going to do recursion. We're going to recurse down and we're going to 2. And we're going to add 3 and 4. We're going to add 1 and 3 to its neighbors. Well, we've already visited 1. We just came from there. But we still want to add it to 2's list of neighbors. How do we do that? So we're going to need to check this visited array to see if we've already visited 1. And we're going to see that we have. And then we need some way to retrieve the address of 1, the copy, so that we can add its address to our output array. Or not our output, our neighbors array. So meaning the addresses of the new nodes, the ones we're creating, those need to be stored in our visited array. That's probably the easiest way. We look up, say, oh, have we visited this? If yes, get that value, put it in our list of neighbors. And that might be good. I think we can get away with a set. Actually, now that I'm talking through this, when I was doing my practice run, I was using a dictionary or an unordered map, and I was using the values as keys. So then that gives us a couple of things. Do we care? You can talk about little micro optimizations for correctness, and maybe I'm thinking too much into it. I don't know if it's pointers. I think in C++ usually take 64 bits. These integer values are 32 bits. So if you use a dictionary and you use the integer values as the keys, you can shrink the key size from 64 to 32 bit. Does that matter? Probably not, because then you're still dealing with some. Are you actually? C++ is big on zero overhead abstraction, so yeah, I might. Well, no, because you still have to store the address anyway, no matter what. No matter what, you have to store the address. I take that back. I'm going for it. I'm going to use a set, and make sure you use unordered set. Unordered set. Did I spell that? Unordered set. Unordered is specifically hash based, versus if you just used like set, like without the unordered, like this, that will make it, I think, tree based, some kind of tree. It'll be logarithmic lookup time because it'll be ordered by key. You want unordered so you can get that good hash run speed up. Okay, we've got our visited set. So now we have to do our work. Okay. Check for edge case, or it's not even just an edge case. So yes, it's an edge case, but it's also our base case, because this is going to be a recursive function. So you need a base case so you don't recurse forever. Simple enough. So we got that done. So now the structure of this is going to be, we're going to do work, add something to the visited array, and then we're going to do the recursive logic. So first, do work. What do we do? Since we're storing the copied node, the address of it, we need to actually make that first. So node. I'm gonna call it CPY. So I don't that hopefully that won't clash with anything like a. I don't know if there's like a standard library copy function. Probably not. I don't know. And then use a new keyword. Since they're it's basically linked lists. We're doing some dynamic memory allocation. We want them to persist even after the function ends. So we have to use either malloc or new. So we get that persistent heap, on the machine heap memory. And yeah, it's technically a memory leak, I guess, but that's what we want. So new node, and then we give it the value. So node val. All right, we've got our new node. Let's store it in our set. So visited dot insert copy. Got the pointer. Okay, now we need to do our, it's gonna be a for loop going through each of the neighbors, simple enough. So let's figure out what we want to do with that. So for, what's in the neighbors arrays? It looks like it's an array of pointers. So I'm gonna say for, uh, so if we go through, yeah, for node pointer, I'm gonna say n for neighbor, n node neighbors. What do we do? We're gonna need to get some kind of address and either, if it's existing, if it's in our visited array, add it to our list of neighbors. If it's not existing, then we need to create it by recursion. So let's okay, I'm gonna declare a pointer here instead of declaring inside the loop. It's a little more efficient. It kind of depends how big the array is and if you care or not. It's not great to declare point. All right, let's declare the verse with node pointer. I'm gonna call it C for like copy or child. I'm keeping the variables short because they're the children, and then the longer the parent nodes get the longer name, the big daddy nodes. All right, so C. Actually, we need to check if what. First, we need, all right, so the syntax to check in C++ prior to the 2020 standard is to use what I think looks like a linear time thing, but it's not. Under the hood, it's not. So I'll see if I can get rid of this auto and remember what the data type is, but it's something nasty because it's going to be with like iterators. So auto, what is it? The check, I'm going to just call it check equals, and it's going to be visited, checking the visited array, visited dot find. And we're seeing if the copied address. So it's gonna be, oh, you know what? Yeah, this is why I was using an integer as a map in the testing. The reason being, right now, we don't really have a way to retrieve the address of the copied thing. All we have is the value, and it's important that the values are unique because that means there could only be one possible node because we're checking in our visit. Okay, yeah. Right now, all we have is just this. So what can we get from it that has, a commonality with our, the ones that we're creating? Okay, so let's go ahead and change that. That's right. Okay, thinking that through. So it's gonna be unordered map, and it's gonna take integer keys, and it's gonna have node pointer values. So copy, instead of insert, it's gonna be visited node val equals the copy pointer. There, okay. So that's little better. So then we do our check. So if check, if it doesn't exist, then it returns. So these are iterators. This find returns an iterator. And if it does not find what you seek, if it does not find what you seek, then it returns iterator to the end, which is like one past. End is like a non-existent null iterator, but that's what it returns. So visited end. All right, so that is in. Okay, so if it is in our set of visited things, so check is okay, then this check is an iterator to kind of a pair. It's a pair of a key and a value. So the way you access the value is you have to dereference the iterator, and that gives you a pair. And from there, you have like these first and you have second. So what first gives you is that'll give you the key, second will give you the value. So the value is our pointer. Good, that's what we want. So and then else, if it is not found in our visited array, we need to make it. So then C is gonna be clone graph, our recursive function, finally. And then we call it on, we're gonna call it on N because, well, C has nothing in it because it's empty. So we need to call it on N. And we're gonna clone that. And then lastly, that's our loop. And then at each iteration of the loop, after we get that check, we're gonna add it to our neighbors. So copy neighbors dot pushback. See. The big daddy copy gets the little copy added to its list of neighbors. And then lastly, of course, we're going to return our copy. So return, which is the whole point of it. And then at the top level, it's going to be, yeah, that's our final output. So I'm going to talk about runtime. And I'll give it a run for syntax first, because this is already kind of a long-winded explanation, just to give you like a sanity check. And then I'll do the example. So runtime. We said it was linear, said that up front. So it's O of, and this time it's a proper linear. It's not like a tree linear where it's like the graphs and edges are the same. It's linear, where the edges affect the runtime because you're doing an iteration of the loop, and you're doing that constant work for each edge as well. You're just not recursing if it has a bunch of edges and things are all neighbors with each other. You could end up with like a clique where everything's connected to everybody. So this is the syntax. V is the set of edges. V is the set of nodes, the vertices. E is the set of edges, and the bars mean the size of the set. Which you could also call, well, there's also a convention O of N plus M, I guess. Yeah, pretty much. And yeah, because it's just for depth first search. And it's also linear space because you're still allocating a stack frame for each of the edges each time you recurse. You're just not going to like recurse even further. But so it's like one stack frame additive. So it's not per edge per vertex, it's per edge and vertex. And then, yeah, okay, so that's time and space. Let's just, I'll run it and then do the example. Come on, what did I do? I didn't put the argument in find. Visited, find, and val. Yeah, that is, that's important. Boom. Well, those edge cases don't matter, but all right, so we've got that. Okay, let's step through it. Let's go, baby. Input, starting with this. Um, adjacent. Oh yeah, it's adjacency list format. Meaning, what kind of input is this? First node. Okay, so this is 1, 2, 3. Okay, I see what's going on. So let's write this out a little cleaner. 1, 2, 3, 4. This is what it is under the hood. This is the adjacency list format they're talking about. That's our input. Let's go ahead and do it. So we've got our list. I'm gonna go. So first we start off at 1. We got our visited. Let's make the visited array. So visited. We start off. 1 is not null, so we're not going to return that. We're going to make a copy. And then that copy is going to be of, it's just going to be of 1. And then we add 1 to our visited array as well. So this is the copies. And we want to copy the graph. So let's go ahead and put that 1 there. All right, what do we do next? For each of the neighbors, we're going to check if 1 is in visited. Or yes, each of the neighbors, so 2 and 4. Is 2 visited? No, it is not. So we're gonna get, that's not gonna be equal to the end. So meaning we're gonna call clone graph on this end value. So we're gonna clone graph on 2. We're currently working on 2. I'm gonna put up a star there for that's where we currently are. All right, what do we do? 2 is not null, so we're gonna make a copy of it. 2 exists now because we call this new. And then we also add it to our visited array. Visited 2. For node in the neighbors, we check. So now we're here. Is 1 in our visited array? It is. So we're going to do this. Check is not equal to null. So then we're going to get the pointer to 1. We're going to add 1 to our neighbors. And then we push that back. And then we continue. Okay, so now we're at 3. Looking at 3 neighbor. And it's similar. This time it's not in the visited array. So we are going to make it and recurse. Actually, no, we're just going to recurse and then on the next step. So now we're here. Yeah, so our stack is sort of going to be like going down and then we'll pop back up as we go. Or maybe I'll figure out another notation if that gets confusing. All right, so we're at 3, 4. All right, we have 3 has here. It has 2 neighbors. Is 2 in our visited array? It is. So we are going to add, we'll first add that. And then 3 is now visited. And then we're going to add 2 as a neighbor. Okay, next iteration is 4 a neighbor. It is not. So we're going to recurse on it. 4. So now we are here. And hopefully there's no more like crazy recursion. No, or at least not a lot of it. We're at 4. We made it, we added it to our visited list. 4 neighbors. So now first neighbor is a 1. 1 is in our visited array. So we're gonna do this. We're gonna retrieve the address of our copy of 1, and we're gonna add it to a neighbor. And next one is 3 is in our visited list. It is, so we're gonna add 3 as a neighbor. And then that's the end of 4. So we pop back up to this 3 case. For 3, now we're coming out of this line and we're adding 4 to our neighbors. And then that is the last neighbor, so we return that 3. So now we're back up here. 2, we're coming out of also this line, and then we get that back. So then we're going to add that to our list of visited. And then that's the last neighbor from 2, so we pop back up to the next frame up. And then 2, we're coming out of this line, and then we add 2, that 2 node, that new one, as a neighbor. And then we move to 4. So now we're at this 4. Is 4 in our visited array? It is. So we're going to retrieve its address here with this line, and then we're going to add that to our neighbors. And that is the last neighbor for this one node. And then there's no more stack frames. So then we are going to return. We're going to break out the loop and return this 1. And that 1 is our, so yeah, how does it look? So 1, 2, 4, 1, 2, 1, 3, 3, 2, 4, 4, 1, 3. Cool. That looks good. That looks right. And they're all copies. So yeah, there's our example. I'm going to go ahead and submit and call that one good. Fingers crossed. All right. Boom. Mark it off. And good night, ladies and gentlemen.